Hi, everybody. Welcome to the fourth breakfast in our FREng Net Zero series. I want to just introduce our chair, Kathryn, who is from WattLogic and also on our electricity board. She's worked in the energy industry across energy and utilities, financing and operations, and she will be the chair today, and I'll let her introduce the speakers. Kathryn, over to you.
Okay.
Oh, introduce ourselves.
Perfect.
Thanks, Kathryn. So I'm Kathryn. I work as Grid and Regulation Manager within Scottish Power Renewables. Scottish Power is a part of the wider Iberdrola Group and the biggest utility in the world promoting renewable energy. We are 100% renewable in our business, and my role on a day-to-day basis is to look after grid compliance, ancillary services, and also drive policy and regulation within the UK sector. With you, Tim.
Thank you. Yes, I'm Tim Green from Imperial College, London. I research on the future form of electricity networks. My background was in power electronics, and I seem to have been saying for a long time that power electronics was an increasingly important part of the way that electricity systems will behave in the future, and it seems like we're there now. So my focus is on how you control the future system and what sorts of equipment and facilities you need to do that.
Hi, I'm Will Wilson. I work for National Grid ESO. I've been in the industry 24 years as an electrical engineer doing lots of different jobs. My current one is Operability Strategy Manager, which means we do try to ensure we hit our 2025 ambition onwards, and make sure there's kind of the rules, tools and assets in place to be able to deliver that and keep the lights on.
Okay, great. So our session today, we're going to be talking about grid challenges that are inherent within the energy transition. So most people are pretty familiar with the challenges that come with managing the energy side of intermittency. But today we're going to focus on the grid stability side of intermittency. When we think about our electricity networks, they've pretty much grown up out of the generation that we've grown up with. So conventional generators generate electricity because you have one magnet rotating inside a magnetic field of another magnet. And as that rotation happens, your current periodically changes direction, and this is alternating current. And these generators all rotate at 3,000 revolutions per minute, which gives you your 50 Hertz frequency that you have on the system. If you don't have enough supply to meet demand, then the action will be that you slow down the speed with which the turbines rotate, and then the opposite is true if you have more supply than there is demand. And because these turbines are big, heavy lumps of machinery, they don't really enjoy having their operations changed very much. So they resist the changes to this, and this is called inertia. If you think about wind and solar power, now obviously they're not generating electricity in the same way. In fact, typically they're generating direct current that gets fed into the grid using power electronics. And historically, those electronics have been pretty passive. So they've sat there and they've looked at this lovely waveform that's being generated by all these big turning things. And if it looks normal, they just go happy days and inject their electricity. And if it isn't, then they don't. And so as you start replacing these conventional generators with intermittent generators that are operating in a completely different way, all of the things around how your system works, you need to maintain that frequency, it becomes more difficult. And those are the challenges that we're going to be discussing today. A little bit of history that I find quite amusing is that in the late 19th century, there was a large battle between Thomas Edison and Nikola Tesla, known as the Battle of the Currents, where Edison thought that the electricity grid should be centered on direct current, and Tesla wanted alternating current. And Edison and his cronies went to some fairly extreme lengths to persuade people that direct current was better, so they were publicly electrocuting horses, and they set it up so that the electric chair in the US was operated using alternating current to persuade people that this was a super dangerous thing. But in fact, Tesla won the argument, and that's why we've all got AC grids now. you might think that we would have preferred a different choice, but we're obviously not going to go back. So we're going to instead talk about how do we manage this transition when we've got these very different physics starting to happen. So I'm going to start with Tim. Yeah, so I was wondering if you could sort of develop this point a little bit about how these challenges are really emerging and starting to affect the electricity network as we move on these sort of rotating machines to inverter-based technologies.
Yeah, thank you. So you gave a very good overview of how we've arrived where we are, and I think that the co-evolution of the grid with the generators at the end of the 19th, beginning of the 20th century is an important kind of thing to bear in mind, because those generators, as you described, you can write down a set of equations that describe their physics, the way the rotating mass moves, the way the voltages are induced in the windings, and that's kind of consistent across different scales of generator and between different manufacturers, and the designs for those generators have converged and become consistent. And so grid operators know how to model the system, and they know what those generators will do when they're disturbed, when the voltage is depressed in a fault or a generator is lost and the frequency is perturbed. And we have co-evolved so that we know how to set up a generator to react properly when another generator locally disconnects and the frequency begins to dip. We know how to cause the other generators to produce power. And when we turn to the inverters, with the things that do DC to AC conversion I described, you're originally generating DC in your solar panel, you want to connect to the AC. Those devices are really defined by the way their control software operates. There are some hardware limits to do with the semiconductors and the limits on the current they can produce, but essentially they're software defined. And that makes them opaque, really. And the software is the proprietary property of the vendors of those systems. And so they do a limited disclosure. And that's part of what makes it difficult for a system operator to gain the assurance that all the right behaviors are in place. And I think you made an interesting additional point in there that initially the job of these inverters was simply to synchronize the grid and produce the power that the original source produces. So they participate in the energy market, but they don't contribute the services that help a grid control frequency or control voltage or manage faults on the systems. So in a way, we were happy to give them a free ride. They provided energy, and we could ignore them, basically just think about the conventional generators and how the grid operated. And we seem to be beyond that now. Now we're hitting times when there are so few conventional generators scheduled to run in the energy market that you have to constrain some of them on and constrain some of them off to make sure you have enough of the inertia and other things you talked about. And we seem now to be, I think, going through a rapid process of rethinking how we control the features of the grid, getting beyond this idea of having to constrain on some conventional generators to start thinking of where we get our services from. And also thinking about whether the things we've grown up with, like the idea of inertia is key to controlling frequency, is really true. We want to control the frequency, but does it have to be through a thing we call inertia? Well, I realize I've said probably a bit too much, but one more thing, there's a scale change as well. We've got this couple of hundred generators to hundreds of thousands of solar panels and tens of thousands of turbines. There's this change in the scale and the complexity of the system.
Yeah, and it's interesting that you're saying that, because there's a region of Australia, the West Murray zone, where actually they've hit the limits of inverter-based technologies that can actually connect to the grid until they do some significant strengthening work. So it's not just that it's presenting challenges of having to curtail generation that's already on the system. It's actually preventing new generation being added in some areas. And when we spoke last week, you mentioned some emergent behaviours on the grid that were presenting some challenges. I'm wondering if you could talk a little bit more about that.
Sure. So some of it is what you've just mentioned. In some grid areas, we find that when the solar panel or the wind turbine reaches a particular operating condition, particularly when there's high output in then an oscillation develops. Instead of producing a steady flow of power, that power fluctuates, typically quite a low frequency, maybe around 8 times a second, something in that region. And the early examples of these that have emerged in Australia and across North America have really been grids that are quite weak, where the solar farm or wind farm is on a long connection. Maybe the grid is switched into an unusual state, so some of the transmission lines are not in service and the grid is further weakened. I think we're starting to get on top of that weak grid oscillatory behavior. But we see others now. There's an event that ESO in the UK observed in the north of Scotland in the summer of 2021, where an 8 Hertz oscillation developed on the bus. You can see that the voltage on the bus, instead of being 400,000 volts, was 400,000 volts with an oscillation of 40 kilovolts on top. Now, that is an example of an emergent behavior. None of the planning studies foresaw that such a behavior would happen. And in the control room, they were able to take some action to turn up a hydro station or turn down some wind in the area and get on top of that oscillation. But the difficulty is if your system modeling is not telling you that that behavior might be in there, how do you know that the solution you found is going to work consistently when another operating point, a high wind day or a high sun day or some combination of events, you don't know if that behavior is going to return in some fashion. We're beginning to see that around the world. And I think it's a real challenge now for the interaction between the vendors of these systems and the system operator to develop models that not only let you replicate that problem so that you can try to understand it, but give you some design guidance. What is it that you can do to sidestep that issue or avoid it from emerging? And can you be assured that you can do that in all your operating conditions? That is a real problem.
You just mentioned the solution in that particular case, although there's a sort of a tactical solution, if you like, being to make adjustments with generation. Do you think this is a generic approach that should be taken, or do you think there are other options within sort of grid equipment that could be addressing these problems?
In that specific example, I think the feeling is that that's not a satisfactory solution in even the medium term. It's a way of stepping around the problem that was immediately observed. But we need to find more fundamental ways of modeling the stability of the system and gaining assurance of it. And it's problematic because the manufacturers are not able to do a full disclosure of what the software does. They may give a black box model, that is, they compile some computer code that will replicate the behaviors and put an input in and observe an output within the system model. But it's not letting you understand what the phenomena are underlying the instability. I think that's a resolvable issue. There's research work going on trying to find ways of probing the system to look for emergent behaviors and using those probing signals to characterize the system in a way which you use a root cause analysis. I think there's a more general point in there about how you solve problems. The electricity is a system with a lot of complex subsystems within it. If you optimize a subsystem to get a low-cost solution, so you design your lowest cost grid, you're likely to throw cost somewhere else. You throw it into the inverter-based resources. So the question really is, do you make the grid fit the way inverter-based resources run, or do you make the inverter-based resources fit the way the grid has historically been designed? And in a way, those two extremes are both poor. We're looking for a system solution which we try to work out what changes in the grid plus what changes in the IBR get us to the lowest cost solution. And I think my favorite example of that is the way we protect our systems against faults. So a fault might be a tree hitting an overhead line, causing a short circuit. Traditionally, the generators dumped a huge amount of current into that short circuit. That huge current was quite readily detected, so you could detect and locate the fault. And then you could open circuit breakers to remove it. With the inverters, because of the presence of the semiconductors in there, you can't let those very high currents flow. They would damage permanently to the inverter. So they produce much less fault current, which makes detecting and locating the faults that bit more difficult, substantially more difficult. So do we require all of our transmission distribution owners to rethink the whole way they do protection, the way they locate their faults and open circuit breakers? That's going to be vastly expensive and probably breathtakingly difficult to do with the number of protection devices across the network. Or do we say to the inverters, you must produce at least as much fault current as a conventional generator? That's going to throw enormous cost into the inverters. And I think it's an illustration that as an industry, as a sector, we have to come together across the developers of the wind farms, the OEMs, the grid operators, and try to find out where does the solution lie that minimizes the system cost, and then how do we define a set of grid codes and connection codes, system services that drive us in that direction.
I want to be quite cheeky and ask just one additional question here. So, I mean, you mentioned that one of the challenges is the lack of transparency with the software. I mean, do you think there's an argument for requiring that to be transparent to TSOs?
I'm sure the TSOs and the research community would think that was a terrific idea. I think there is genuinely a need to protect the intellectual property of the vendors. They put a lot of effort into coming up with the best possible performance for their wind turbine and so forth. I think what we have to work towards is a way in which there can be an information exchange between either the developer or vendor and the system operator, where we can pass information across the boundary there in a way that lets the system operator have enough insight into the behavior of the wind turbine to do its root cause analysis without revealing all of the specific innovations that the manufacturer has. I think there's a route through, essentially the route through the mathematics to have a way of information passed in that lets us do it.
Great, thank you. Okay, Will. So we've just heard from Tim some of the technical theoretical challenges, if you like, from National Grid's perspective. Can you talk about your perspective on this and how you're observing these challenges?
Can I just say, Tim, thanks very much. That's awesome.
You can certainly say that. Thank you.
That was, yeah, completely agree. So how we as kind of the ESO kind of look at the future and kind of figure out what we need to be able to ensure the lights stay on is we kind of base everything on something called the FES, if you come across it, future energy scenarios, that kind of feeds through. So that kind of sets our scenarios, and then we look at all those scenarios. There's lots of documents out there that do it, NOAA, ETIS, operability strategy report, market road, loads of them. Anyway, so what they do is they kind of look up at these future energy scenarios and make sure that under any of those scenarios, we've got the capabilities, rules, tools, and assets in place to be able to operate within that kind of. So it kind of sets a kind of a bandwidth, or whatever you want to say, of what we need to be able to cope with. So underneath the FES is kind of the top line document that's setting your baseline, and then everything else is looking at that baseline to figure out what we need to do to be able to kind of ensure that the lights stay on for that baseline. I would like to use this opportunity to highlight two docs that are probably very relevant to everyone in the room. There's a document called the Operability Strategy Report. That's saying what the system need actually is, and that's published once a year, and there'll be another one published in December. So that's saying this is what we need from a system point of view. And then there's the market roadmap, which is looking at that system need and then turning it into what are the markets that we're going to be creating, what are the market opportunities for kind of market providers to engage to be able to provide those services. So I think for this, those are two very relevant documents for kind of this session.
Okay, perfect. So I guess when you're taking that information from the FES, I mean, given that National Grid isn't, you plan the system, but you don't plan the system in that sense. You're not deciding what the generation mix is going to be at any time. You're sort of inferring what it might be under different pathways. Can you say a little bit more about how grid behavior changes look in practice when you're looking at things like falling inertia, short circuit level, and reactive power, and how that varies across the, I don't know, not without getting into detail of the scenarios, but from one end to the other, if you like, the spectrum.
Completely. I think Tim said that really well. But basically, we've got four kind of big macro trends kind of going on at the moment. We kind of got, this is where I'll probably forget one, so apologies. You know, we kind of got generation no longer in the same place. You know, the old days, it was ahead of the kind of coal pits, whatever. It's now moving to kind of where the wind resources are, where the sun is, all that. So it's kind of moving the location. And that effectively means that it's kind of going to the edges of the system. You know, you see quite a lot of generation in Scotland or offshore wind and stuff like that. And so that causes, that's an operational change for the power to flow more over long distance and stuff like that. This increase in renewables is also, there's kind of two factors here. A kind of increase in renewables is kind of not as controllable in the old days. You know, renewable generators generate when it's windy, when it's sunny. And the old days, you pumped a bit more gas in, pumped a bit more coal in, let the water run. So it means it's not as controllable, and that's not great when you've got to match generation and demand second to second. And they're also more variable, you know, renewable sources. In the old days, you could like stick out at 100 megawatts, whatever, and just hold it there. Nowadays, that doesn't happen. It kind of, when it's windy, they blow. When it's not windy, they don't blow. And the last kind of macro trend that's happening is kind of things like, as Tim said, it's kind of going from synchronous. We've talked about going from synchronous to asynchronous, which causes all the challenges we've kind of highlighted. Right. So those are kind of the macro trends. How that turns into systems is it means that we think that in we think that as kind of 5 challenges, voltage. Yes, engineering terms, they're all interrelated and it gets really complex really quickly. But in a way to simplify it out and make it more manageable, we kind of divide those challenges up into kind of 5 areas: voltage, stability, frequency, thermal, and restoration. What do I mean by that? What I think we're focusing on today is voltage and stability. So I'll focus on there. But what does that mean? So as you've got your generation going to the extremes of the system, that creates thermal challenges because you're fundamentally flowing the power more. But that also means it creates voltage challenges because most of the system, you know, if you're flowing power a long way, that means you need voltage support kind of in the to be able to flow that power. But that also, in the old days, you'd have generation kind of more distributed and the generation would support the volts. When you have kind of renewables kind of going to the edge, that creates generation holes. So you're looking for new sources of voltage support to be able to prop up the volts. So kind of voltage is a challenge. Right, stability. We've talked about stability before, and I think Tim really good. What I could improve on that explanation. But stability, they are absolutely the same challenges. You know, going from a synchronous generators to asynchronous means you kind of got, we think that as 3 main challenges. Kind of dynamic volts. What that means is under fault, the volts drop during the fault for kind of the sudden millisecond. And if the voltage isn't, you know, sufficient, as Tim alluded to, what then happens is other things connected to the system struggle to kind of inject the power. And that's a real issue because, you know, you've got a fault over here that subsequently kind of cascades to other things because they're struggling to see the voltage and squirting the power. So kind of we call that dynamic volts. And that's very related to kind of short circuit fault level, which is the other one. As Tim alluded to, the short circuit voltage levels are dropping. And that's a real issue as well. It means it causes problems under fault for voltage, but also it causes real issues with protection. You know, as Tim alluded, if the protection doesn't operate and can't discriminate a fault, that's a really bad thing. You know, 400 kV is very, very dangerous, quite frankly. And if you can't switch off a fault on the network, that's just not going nowhere with that. And so we've got short circuit fault level. Oh, inertia, yeah. You need kind of this inherent heaviness in the system. We're learning to cope with less and less and less. You need this inherency. So when you have a fault, you actually have time before for your frequency services to kick in. If you don't have time because you've already lost the system because you don't have enough inertia, that's a bad thing because you need the kind of the heaviness in the system to be able to kind of give you the time to be able to respond. So those are kind of the things that we think about mainly to do with stability. I think Tim introduced a really interesting kind of another one, because there are, there's always complexity out there. The oscillatory behavior kind of coming up in Scotland. Absolutely. As we kind of drop the inertia levels of the system, as we operate in these kind of much lighter systems with much more renewables, we are pulling back the rug. We are going to find kind of these problems that were masked, quite frankly, by these kind of heavy inertia systems. And no doubt, unfortunately, as Tim alludes, we're going to find more as we go to a more renewable system. So it absolutely is a challenge that that needs facing.
And so obviously you've been doing a lot of work around trying to understand how these different behaviours are emerging and how they're developing in the grid. Can you talk a little bit about how those monitoring tools are being developed to help you understand what's happening?
Can I put it a bit wider, because there is so much going on? Because there is honestly the pace of, I've been in the industry 24 years. I think I was saying to somebody, 24 years, the pace of change is massive. It's really exciting time to be in the industry. But there is so much going on. In the old days, National Grid, there was a tendency to National Grid to kind of go into its bunker and come out with a solution. That doesn't work any longer. It never worked in the first place, but let's gloss over that. The only way we solve these challenges together with industry, and there is lots of work going on out there, lots of it. You've got the pathfinders, stability pathfinders, voltage pathfinders. That's hundreds of millions of pounds of investment going to solve these problems, the challenges. Initially, we did it through sync comps, because these are world first. These are absolutely breathtaking and like kind of breaking new ground. Initially, we did it just through sync, the technology we knew. Stability phase 2 kind of lowered the bar and said, right, asynchronous type technologies can also be providing these services, which is awesome. So we are absolutely inviting asynchronous type technologies. We're about to do phase 3, which blatantly will include a large part of asynchronous technologies, providing kind of the answers to these problems. So this is absolutely something that a renewable technology can help provide the answer to. There's a challenge coming, and asynchronous can help provide. But in addition to that, these challenges aren't in isolation. You talk about stability, but stability and frequency are highly connected. You're trying to keep the system stable enough for the frequency response to work. So what we've done in the frequency space massively impacts inertia, for example. And so we've completely overhauled kind of all our frequency products. In the old days, 15 seconds for kind of primary response. We lost the system in 15 seconds. That's just not acceptable. So you've got DC, dynamic containment. That's like a sub 1 second type response. And you couple that with changing the accelerated loss domains. These are kind of these are relays within kind of embedded DNO networks that trip. That means the system is now fundamentally much more secure than it was. And you couple that with something called FREng, frequency risk and control report. And that's a paradigm shift in the way kind of these things are managed. Absolute paradigm shift. And you've seen the costs. This is kind of combining all these different pieces of work together. And you've seen the costs, the operational costs have dropped from hundreds of millions down to kind of less than 50 or whatever it is at the moment. It's massively changed, just because what you've done is we've recognized that the system is changing. The old ways of operating the system is not working, and we've kind of adapted. But that's not to say we've not got to carry on doing a lot more adaptation and kind of bring it on to the things that you're talking about, kind of inertia monitoring. Absolutely, those are kind of the new areas that we're going to. We don't have all the answers. 100% we don't have all the answers. And we're engaging lots of very clever people we've got to help us find the answers, because as you say, you mentioned that the modelling capability isn't there. You're right, it's not. It's because these are all very, very new challenges the industry has got to face. And yeah, let's solve them together while keeping the lights on.
Okay, well, that's a very nice sort of flow through into the generation side and how generators can contribute. I know Tim mentioned earlier that there's this as effectively a chicken and egg almost with, how do you marry up what the system requires on one hand and what manufacturers can provide but obviously manufacturers aren't providing it until they identify the need, and it can become a little bit circular. So how do you see that, and do you feel that there's a good enough understanding of the, I suppose, the direction of travel to sort of make that into a virtuous circle?
Yeah, so thanks, Tim and Bill, really well explained all the challenges. So maybe I can focus more on the solutions. But I think what we sometimes suffer from in the industry, we are all guilty of it in a way, is a nostalgia of synchronous generation. We had these big taking plans. They gave us so much inertia and short circuit level. How are we going to survive without them in the future? Well, converter-based generation do not really care about inertia or short circuit level. Like we install large offshore wind farms that the offshore grid has pretty much no short circuit level and it still operates. And so challenge here is, as Tim rightly pointed out, do you change the grid to suit the renewable or just to fit how converter-based generation works? Or do you change converter-based generation to suit a grid that's based, whose operability definition is based on synchronous generation? I think you rightly pointed out, none of those extremes are the correct answer, so we have to find a middle ground. Now, what the ESO has done very well, and Bill has already alluded to it, is that for years now, since this transition started, they started publishing future energy scenarios, system operability framework, markets roadmap. They came up with 7 or 8 new markets in the last 3 years, which is tremendous work. However, I'd like to highlight that one of the missing pieces in this is all of this are still very focused on what we lost and how we can backfill it, rather than how it's going to work in the future. So there is very little to go on for manufacturers. So manufacturers are not only the people who are protecting their IP, they're also people who want to make money. They want to make profits, and they would respond to any call from the system in terms of a grid code change. So we didn't mention grid code here. I'll come to that. To a grid code change, which can mandate services. They will respond to markets, and so Will already said that in Stability Pathfinder 2, you asked for short circuit level from asynchronous generation, and the market responded to that. So it is what are we really asking for? And I think the ask has been very much focused on what did we lose, rather than how the system will behave in the future. So unless we can change the question, we're always going to find an answer which is more kind of fitting renewables to the grid, rather than moving a bit to the other side and saying maybe we need to change grid operation to fit renewables or kind of to match the converter-based generation behavior in the future. I'll highlight one point here of how we vary in GB from other countries with similar challenges. And when I say other countries, I will speak specifically about Ireland and Australia, because both of them are island systems, so they're not heavily interconnected. We can't really compare ourselves to US or Europe because the grid itself has a lot of mass. Now in Ireland, what they have is called the synchronous system non-synchronous penetration level, which gives a percentage of non-synchronous operation on the grid at any given time, as compared to the total demand and how renewable energy is meeting. What we define here in GB, or an equivalent of it, is called zero carbon operability. Now the challenge with zero carbon operability is still holding on to that feeling that we still will have synchronous generation that will give us inertia and short circuit level. And I do understand why we are doing that, because our future energy scenario is not going to be 100% renewables. There will always be synchronous generation on the grid. However, that is also giving us probably a false sense of comfort, where we think that we don't have to really understand how converter-based generations will behave in the future. Now, going to Australia, what the Australian system operator AIM does, and it's a bit more extreme, and probably we shouldn't go there, but what they do is they do detailed modeling, and we spoke about modeling a lot. The Australian system operator does a very detailed EMT modeling just before the connection into the part of the grid, and they tell the generator what they need to do and how they need to behave to connect there. Now, we have only recently passed a grid code change that requires us to do that modeling, and I do understand there are lots of challenges with models, and the project comes in a minute, but we are late there. We haven't started doing that, what we should have done 4 or 5 years ago. So although I completely appreciate the challenge on hand, and I completely appreciate that ESO has done a lot in that area, I think that nostalgia for synchronous generation that needs to go at some point. We need to understand that our future depends on understanding of vast quantities of renewable generation connecting to the grid to be able to correctly define the operative challenges.
And so I would like to kind of ask a little follow-up question on that, because if you would like National Grid to define, say, grid code requirement for connection at one point, does that not further embed this nostalgia that you're sort of complaining about in a sense? Should it not be coming from the other side? Because how does National Grid get the visibility on what inverter-based technologies can deliver if they can't see that? If that makes sense.
Yeah, no, absolutely. I think let's all acknowledge that modeling is a challenge, and we have all spoken about it and we have all addressed it. So modeling has been a challenge in the sense that it's been very hard to understand how inverter-based resources really work on the system. And on OEMs have not been very forthcoming with it, which has been a challenge. But there's a lot of research going on. There's also talk of digital platforms where OEMs can essentially plug in their models, and the studies can happen in that sphere with them controlling the parameters. And that would give you a visibility of the interaction that will happen in the grid. Now, I do admit it's really difficult because each part of the grid, even in Great Britain, if you take Scotland, the behavior might be completely different than in England. So I think where probably ESO can do more, or the academia and OEMs and developers can help more, is to improve the modeling and start studying what happens, what's the behavior of the system when it's 60% asynchronous, 40% synchronous, what's the behavior when it's 70% asynchronous, 30%. So this is what I was referring to, the Irish SMS limits. What's the behavior when it's 95% asynchronous, 5% synchronous? And if you have the studies to hand, then you can make an informed decision or form an informed view regarding the transient behavior on the system. So we'll already refer to oscillations in Scotland, which are happening right now, but there's no grid code that talks about oscillations and what inverters are supposed to do, and except for the grid forming part, which is not mandatory, what inverters are supposed to do during the fault right through when the oscillations happen. And their grid code can help, because if you understand how the system is going to behave in the future, and you can define what mitigation measures you require in the grid code, it doesn't matter what technology is providing. You can create generation or create converter models and software that can help mitigate it, or even synchronous generation that can help mitigate it. It's just that a grid code is still lacking in defining a lot of this transient behavior. And that's why the connecting generation doesn't really know what it needs to do when it connects to the grid.
You mentioned different levels of synchronous versus asynchronous or non-synchronous generation, and I know when we spoke the other week, you were talking about having an understanding of even if we had 100% non-synchronous generation, even though that's not likely to be the actual generation mix. Can you talk a little bit about why you think it's important to understand that scenario?
You're very right, and the National Grid will be very right defending the position that probably the generation mix will never be 100% asynchronous. 100% renewables, we have hydros, we have nuclear, we will have CCUS in the future. No doubt there will be always synchronous generation in the mix. However, it's a bit like, you have to give you an analogy, is saying that Titanic is unsinkable, that's why we don't need enough lifeboats on it. So it could be because we are connecting vast amounts of renewables, and the prediction is there will be 50 gigawatts of offshore wind. What if there is a scenario where a part of the network is islanded, say Scotland suddenly disconnects from England for one or the other reason, there is a big storm, I don't know. We have seen some things like similar things in Australia, and suddenly we are left with a big part of the grid, which is 100% renewable at that point, because there is no nuclear there. Maybe the hydros are not working that day. So, but what do you do in that situation? You are pretty much reaching 100% renewable. I mean, recently we had also incident in France where the nuclear reactors had to shut down for one reason or the other. That scenario can happen. It's rare, but it can happen. But understanding how we prepare for such eventualities and what we need to do and how we will keep the lights on will give us the right indications of what kind of services or what kind of converters we should be installing on the grid. I know that you can't prepare for all eventualities because then the cost to the system or the consumer will be astronomical and we can't really cater for that. However, studying those eventualities gives you a very good perception of what the operation of 100% renewable grid looks like and helps you build a business case that meets at least those eventualities or they cover those eventualities in one way or the other. Well, I don't appreciate or understand at the moment that we are absolutely saying that there will be never 100% renewable grid. So let's not, we don't need to really study or understand that. And I know there are reasons on both sides, but I do believe that it's not, it won't be that impossible to have 100% because of one reason or the other, because of faults in the system or one of those days when there is a lot of renewable and the grid is connected with silent.
So we've talked quite a lot about and mentioned how inverter-based technologies can be contributing and responding in different ways. I don't know, I think for a lot of people, grid forming is quite a new concept. Could you talk a little bit about the type of technological developments we're seeing in this space and how inverter-based technologies can, through these new grid forming approaches, actually avoid these problems and operate in a different way?
Sure. So grid forming is not new. So if we take grid forming in a whole system perspective, a synchronous generator is a grid forming generator. And the reason being, as everybody has alluded to, it doesn't change its behavior as to how the network changes. It tries to hold on to its reference voltage and frequency and tries to modify the grid to its reference. And that helps in the sense that when the frequency changes or the voltage dips, then it tries to bring it back to what it knows, the normal frequency or the normal voltages. That's a very basic definition of what grid forming is. But most of the converters almost all the converters installed on our grid at the moment are something called grid following. So they don't have a voltage reference. These are kind of current source converters, and they follow the grid. So if the voltage changes, the converter changes its voltage. If the frequency changes, it follows the frequency. So it being the kind of grid follower rather than the grid former, it's not really helping in the case of faults, or it's not really helped to dampen oscillations because it doesn't know anything but to follow the grid. So that's not really just a fault of the converter. It's just that, as Tim said, the role of renewable generation in the past has been just to generate. It's never been assigned a role of really managing system operability or providing stability. So they were all built to just do that. However, recently, after a lot of discussion and hard work on the part of ESO and OEMs and developers, something called grid forming converter has been also introduced. And I would hate to say that it replicates the synchronous generator here because it doesn't. A grid forming converter can be 100 different things. It pretty much tries to hold on to a reference and kind of help the grid stability by either adding voltage stiffness, providing inertial response. So instead of providing direct inertia, it provides something called the inertial response, which is a fast injection of power to control the drop of frequency, just as inertia would do. So it's kind of simulating inertial behavior. And it can also provide short circuit level or fault currents in case of fault, but much lesser than what a synchronous generator would provide. So the grid forming converters can do multiple things to help grid stability in a way that a synchronous generator could have done, but also in its unique way of it being a converter, and it has a much faster and dynamic response. It can actually add to the stability of the grid by providing voltage stiffness, something that has not really been defined in the operating framework right now, but I'm hoping it will come. Now in Australia, they have installed some grid forming converters, and they have had some challenges with it. You have to be very careful when you install grid forming converters because you have to ask the right question to create a converter that gives you the right answer. Grid forming converters can also be a challenge of the network if they're not correctly designed. So all of this comes back to modeling and studies and understanding the system behavior and creating the converter, grid forming or grid following, that can help with the stability of the system, that can contribute to it. So hopefully that answers the question, Kathryn.
Yeah, I mean, I think I'm still back at the whole chicken and egg thing that we started with though. So yeah, I mean, I think it's probably time to see what questions we have from some of the audience. Yes, okay, Jeremy, you're in the room.
Jeremy Nicholson here in a personal capacity, but I declare an interest as an occasional policy advisor to a battery investor. It was mentioned earlier on that we don't need so much inertia as the benefits that inertia provides to the system. And I'm interested to know what alternatives to conventional generation there are from a technical perspective to provide synthetic inertia, whether these be battery based with appropriate power electronics, or perhaps dedicated spinning units that could provide that are part of a conventional power station. What are the technical options there, do you think?
Okay. Tim just gave me the look. Do you want me to start?
I don't know. You go first, I'll if you leave anything, I'll jump
No,
up.
please, I do compliment. So yeah, you alluded to batteries. Essentially, the way frequency works is so you have power generation minus power demand equals to inertia constant multiplied by rate of change of frequency. So when your inertia drops, your frequency changes are more, how to say, more dynamic, and we have a kind of a sawtooth diagram behavior coming on our system. So the batteries can help in the sense that batteries can both manage the generation and the demand side of the equation by either fast, taking in power, importing power, or giving a fast injection of power. So that working with the grid forming converter in front of the battery can hold on to its reference frequency and provide this fast injection, essentially emulating as inertial behavior on the system and keeping the frequency within the range.
Yeah, well, first of all, what a battery can do is deliver power very quickly. So just noticing the frequency has dropped and delivering power quickly, and I think Will mentioned that traditionally frequency response was seen over tens of seconds, and now a battery can come in less than a second. And if it does that, then it arrests the frequency drop faster and without providing inertia, it just makes up the missing power. But it can also, as Priyanka's just said, synthesize inertia power being directly relevant. So I think it's one step back and saying what we want to do is make sure that when the frequency drops, then the deer is deeper than we can tolerate, and the initial rate of change of frequency doesn't upset our protection systems. We have a number of technical ways to shape that response, and it doesn't mean it's necessarily inertia that solves those. So one step back, I think, in the way we define service. I think ESO is defining services differently in a way that help in this direction. A few people, and yourself, have mentioned synchronous compensators or generators that are being retired, take the turbine off and just leave the generator running. And I think it relates to what Priyanka's talking about, sort of our almost emotional attraction to synchronous machines. We like them, they're familiar, we know how they behave, and they give us a sense of reassurance. But it seems like a lingering kind of solution that will have to go one day. It seems keeping big lumps of metal spinning doesn't seem like the future to me. It's reassuring at the moment. I understand why we're doing it. It allows us to increase the amount of non-synchronous generation for a while. But I think again, as Priyanka said, we need to look to the solution. How do we run a system that's 100% renewables, even if we only ever get to 98 on a particular day, but trying to look at what a completely rethought system looks like, where we don't have to rely on synchronous compensators. I think it's something we should definitely be doing. And then, but I think Priyanka also said something very interesting about we need to learn from all the territories of the world where interesting things are happening. So I think there are things that ESO is doing in the UK, which others in the world look to, particularly the power finder projects. AMO in Australia is doing interesting things, but the island of Hawaii, or some of the bigger islands in Hawaii, are pretty much 100% renewables on occasion with large amounts of batteries. don't have to be competitive between these territories. There's a lot to learn. And there's a lot to tell the rest of the world. There are many nations in the world which will very quickly have to increase their amount of generation for energy access reasons and tackle these 100% renewables problems. And we need to push those solutions out globally.
I think so. You kind of highlighted the batteries and synchronous compensators, but what we kind of done with stability path management phase 2 is said this is what we want, and then what you've seen the market do is go right. How can we solve that? And they've come up with lots of solutions. I'm not going to try and list them here because I'm going to miss out on one of them. But if you look at phase 2, that will have all the different types. You have more than batteries, and more than, you have air storage, and lots of different types of technology. But where batteries can really help, and they really do help, is they can provide these super fast frequency response. Without that, we wouldn't be able to be doing kind of operating the system at these low inertias. Currently, the lowest system operation ever goes down to is 140 GBA seconds. What that's, I'm sorry that number won't mean anything to you. But what that means is if the market ever, and it often does, give you kind of less inertia on the system than that, we bring on extra inertia to bring it up to that. But batteries are really, really helpful, because what we are going to, over the next few years, be dropping that 140 GBA seconds, hopefully down to, well, the aim is by 102 by 2025. That's a massive change in system operation. That is really quite scary if you're kind of a system operator, because as you start dropping back, you operate at these low inertia, you do potentially bring out these power oscillations and other problems that we've been highlighting. But that's kind of an example of the things that are happening and kind of the change that are happening in the system. Because if you carry on operating at this 140 GBA seconds, carry on operating that kind of level of inertia on the system, operational costs will just go up. So what I'm trying to say is batteries really help, and they can provide these services. Please engage and sell us your services, because they're the only way we change and operate in this new world. There are other technologies as well, but batteries are really helpful. Thank you.
So yeah, I'd just like to ask you, Will, what your thoughts are about moving away from any form of mechanical inertia on the grid.
I think Priyanka did kind of say, this is where there's kind of a sort of difference of opinion. We look at the FREs for the future, and the FRes has things, CCUS, nuclear provides a huge amount of inertia, big things, they really are. Yeah, don't underestimate, you have a few newtons on the system, that's a lot of inertia straight away. Problem is, if that trips off the system, then you have loads of issues. So that's hard at the moment. But there's other things as well that are coming along. And you get a lot of inertia from the demand. The demand itself provides inertia as well. It's not just generation. The idea, kind of, absolutely, you can get islanded systems. Let's hope we don't island Scotland. That would be a massive.
I appreciate that.
The newspaper's very fast. I don't think the last time we had an island, I think, I'm going to get it wrong, but it was a long time ago. But it's not impossible. Absolutely, it's not impossible. If the system does island, it's a very serious issue. Where you would, So yeah, system splitting is one of the fears of a system operator. Happened over in Europe in 2007, something about that. I can't remember, when a ship went under a line or whatever it was. It's pushed out, but it is a real issue, and it needs careful consideration. And completely agree with everything that we need to figure out what to do.
Okay, so we have a question on the screen then. Okay. So it says, how do you align the time to understand the technical challenges with the pressure to build the grid?
I think
Build more grid faster.
it's quite startling, actually. I'm not sure we've all grasped how quickly we are heading towards a radically different system. Sixth Carbon budget says we will fully decarbonize electricity by 2035. If we need to build things out to be zero carbon every hour of a full year, you've really got to start building that stuff now. and you've got to know what it is you're going to build. So I think that's, on the one hand, quite startling. On the other, I've got a lot of faith in engineers being smart people who can come up with solutions. But it is almost two streams of thought, and I think it's there in the question. We do have some fundamental rethinking to do, and we've got to pair that with some learning by doing. So I think the Pathfinder projects are an excellent idea. Build some things outside of the existing market arrangements somewhat, to find out what solutions can be brought forward when we ask for a service, and look at how they behave. And some of those solutions might look, to my eyes, a little bit old-fashioned, like synchronous compensators. They might be a bit conservative in their approach and not strictly use cost, but we learn a lot, and that needs to be an agile innovation between the thinking and coming up with products, the trying it on the network, and learning and going around that loop swiftly, because we really don't have time.
I would say we have all spoken about it multiple times. It can be set up. Improved modeling and studies just absolutely needed. I think that should be, in my opinion, the top priority, and that means that everybody needs to work together, not just the developers in the SO, but the TO. And as a traditionally, we have all been very, it's my data, I hold on to it, it's my IP. I think that needs to change, whether it's driven by the SO, by regulation policy, that comes as a directive from base or Ofgem. I don't know. It needs to change. It needs to evolve really quick and really fast, so we can start studying all the different situations that can happen. And I've already spoken about Australia, probably they're doing slightly better than us. We need to catch up and get there, but also improve monitoring. So some of those technical challenges cannot even be thought of because they happen in real time as we speak. So where we probably are a bit lacking is the communication infrastructure and how much data we collect from all the generators that are connected in distribution network, for example, and also in transmission network. So it's all gone if it's, distributors, as we said. It's gone far and it's been connected at all voltages. Traditionally, there was no really good comms infrastructure there. So I would say improve modeling and improve communication infrastructure to give us dynamic visibility of the grid, which some other countries have done well. For example, NASTY in US, in terms of the PMU growth visibility they have, the dynamic behavior monitoring they have in real time. Same in Iceland. I think we could do much more there. So we in real time see things happening and capture that, and then understand how to react to. So it's kind of learning by doing that can help as well.
Do you want to talk more about the monitoring?
I think, that those, I completely agree. Learning by doing, when you're in the ESO and you've done Pathfinder with Pathfinder, use that phrase, not, but it's true. It's true. I completely agree. The challenges are immense. It's also challenges in the IT space, as you kind of alluded to, in comms. Not a traditional area where the industry has been that good at, unfortunately, but it's got to get better at it. Otherwise, as Tim says, the pace of change is just going to get overtaken. Everyone's got these digital, I was going to say Alexa, but with Siri, whatever they are. There's so much digitalization. They call it digitalization, decarbonization, centralization as the challenges. Yeah, they are, and they're not going to stop for kind of the industry if we can't keep up. Great time to be in it, but kind of exciting versus quite terrifying at the same time.
Are there any more questions in the room?
I don't know what kind of questions online.
Yeah, I can't read it while it's scrolling next. Okay, so how is system operability affected by the emerging role of DSOs?
That's a great question. I would love to have the answer. We're trying to figure the answer. That's absolutely emerging role of DSOs. Very, very important. Does the industry have the answer? No. Again, I keep on saying that we've got to figure out the answer together. That's a classic one. DSOs traditionally very passive networks. With all this rise in technology, that very much not going to be DNOs for very much longer. Massive amount of work in open networks trying to push this forward. How does that work? Lots of different models. Don't think we've really kind of figured out how it works. Lots of different things, lots of different RVPs going on to try to find answers for each of the different areas. And each of those areas is slightly different, which means that the answer in that area is a bit different. My view is I can't help feeling it will end up by solidifying into kind of a end solution, but what that is, don't know at the moment, because there's so many different versions of what that could be. But yeah, very important, and it does make a massive difference.
I would say that's it's probably the key to solve some of the stability challenges, because we were talking about the scale and pace of change and the number of generating units to connect them. I think it's near, I don't like to use the word impossible, but it is kind of near to impossible for the ESO to have visibility of all those units, and then find an optimal solution or optimal operating situation where it says, if I take so much water service from this and that, then will be the cost optimum of operating the system. So what needs to happen is probably a bit of transfer of power to DNOs, where they look at their local network, which they understand because they have been operating it for they are distribution network operators, and they're called operators for a reason, because they have been looking at their patch, they understand how the network behaves, and they can better utilize those resources connected to their network to help with stability. So give you a perfect example. So a national grid-led project called ESO-led project called Distributed Restart. It's to rethink how restoration happens. So restoration has always happened traditionally top down from a coal-fired power plant or a big hydro down on transmission level to distribution. And recently that has all been overhauled by saying that actually, in order to restore, we need to form power islands powered by DER, so distributed energy resources, connected in the DNO network. And the DNOs have to play a more active role in creating these power islands and providing restoration bottom up. So then when the national grid gets other big generators connected, they can somewhere meet, synchronize, and restore power. So it shows that DNOs having that visibility of DERs and having more control over it will ultimately help with the overall stability and services to the system. DNOs do not have the power to commercially right now negotiate with generators. I don't know if that changes or not, but them having better control over the DERs and helping here so ultimately can help. So that requires more local markets to develop, that requires more visibility of the DERs. And I think that's where the role of DSO is critical in maintaining system stability in the future.
Oh, just very quickly, I think there's two things. There's the scale which we've alluded to, the vast numbers of devices connected that we have to treat as part of the system when we look at operability, and the idea that we can do that as a single system with the ESO reaching right down to the low voltage parts of the network is probably just unfeasible. So many other countries, you look at the United States, it runs as area controls. Maybe we're not going that way, but some way of creating a hierarchy, and certainly local problems solved locally. So if we want to reach down and look at batteries in the low voltage parts of the network, something we haven't really touched on is the demand side. Demand side services are going to be managed and controlled, first of all, probably in the distribution network. So this emergence of distribution system operated to solve as many problems as we can in the local area, and then pass up services into the transmission system looks like the way we have to go.
So in fact, that sort of preempts the next question. So to what extent is there scope for consumer engagement and I assume by this one demand side response in either monitoring grid voltage and frequency or in helping to stabilize it?
Shall I just run that theme for a little bit longer? So demand, consumer engagement and demand side participation or response are going to be extremely important. There are things we will try to solve with storage and by international interconnections, whatever, but when we're trying to match the available resource to the demand, being able to flex the demand and move it to different points of the day is going to be an extremely important part of how we manage that. That, I think, is the primary thing to do, is to allow demand to follow supply to a greater extent, perhaps rather than system control services. There have been several proposals for the ways in which Some domestic appliances, for instance, could contribute to frequency control. So when a large generator is lost, would some devices in your home, like your refrigerator, back off a little bit? It's quite technically hard to coordinate all of that. It's probably easier to go after large batteries to provide those services. But maybe there's a route through to some of those control services. Voltage control is probably tougher. The technical reasons it's much harder to control the voltage from the bottom up. It's easier from the top down, but I wouldn't rule anything out.
Yeah, I think there's been some work done there to encourage consumer engagement, for example, commercial, operators with a large plant or something can really vary demand and help. They don't need to directly participate in the market. They can do that by being the virtual lead partner behind the virtual power plants, which is currently Exxon changed the way, different consumers can provide response services by another lead party, a virtual power plant or an aggregator that takes all this consumer behavior and creates an aggregated response on the grids that has a much bigger effect than from the individual consumers trying to understand how the voltage and frequency is working. So I think there's been work done in that field. It's just that I don't know. I mean, it's been a lot told about changing consumer behavior. I think what is missing in the markets a bit is what incentivizes them to do it. Currently, I think there are a lot of market incentives for different technologies, different developers. There is very few market incentives for the consumer of why they should change and why they should provide this. And I think that's probably the first thing that needs to be addressed.
And can I say, have a look at, so completely agree. Consumers will struggle doing the stability stuff. The very fast acting stuff is just, they're not fast enough to be sub 1 second. So they're more in that reserve space, as we talked about. So kind of helping kind of a slower sort of energy type response. And then, you have aggregators already looking to kind of sell in those services after system examples, suppliers. And for this winter, you've got the ESO putting forward this it's not furniture home store, DFS, dynamic. What I can't even remember what that stands for. But yeah, so completely lacking. At the moment, the market doesn't provide the services, the kind of the right commercial incentives until like 2025, and like you get metering in, a proper half-hourly market. But that's why National Grid has kind of introduced this temporary kind of type service to kind of give a commercial signal for kind of these consumers to start engaging, because in the future, absolutely they are very much part of the solution. It's just unfortunately the market's set up that they don't have the rewards for engaging at the moment, cost efficient rewards.
Yeah, great.
Yeah.
That's a very good question to follow up with you.
Yeah, I was going to say, I mean, this it was something that I'd noted down to mention as well. I mean, the question on the board is, what are the future trends scenarios for energy pricing based on the points that have been discussed? And I think an ancillary question to that is whether energy pricing itself is part of the problem.
I think we have just been taken from a technical to a market-based discussion. I'll just give a very brief answer on that because my knowledge kind of fails when it goes to too much market-based discussion. But we have been discussing energy pricing and the cost of living and everything that's been skyrocketing and how do we really manage it. I think stability and services do play a big role in that because we are still reliant on gas for many things, and I think gas does drive the marginal price, which then changes the price for how the whole system operates. So I don't want to say that tomorrow we should switch up all gas and be cold in the winter. That's not the point, but what I would like to say is that future pricing should reflect some of these incentives that we spoke about, that if consumers to take the right action to help the grid, to manage demand, and also to provide services, there should be visible incentives for them, not just a coupon or a voucher in the mail, but really chunks of, bill coming down, a reduction of actual energy bill to engage that, create that behavior. So there is a big consultation out there called the REMA consultation, where there's a market reform looking at, it's not covering retail, but it's covering all sorts of other aspects things to change the market to better suit the consumer. And I'm hoping that once we find the answers through that, it will actually help drive consumer behavior and bring down prices.
So you completely agree. If you don't have kind of energy pricing, the fares shows the cost just through the roof, astronomical. You know, it's asymptotic. It really is. So you need this. Otherwise, you're building lots of extra infrastructure to cover a very short space of time. You know, so you absolutely need something like this. As I said, Rima, location marginal pricing, all that sort of stuff, been around quite a long time, been discussed. This is kind of the first time, well, in my mind, that it's kind of actually starting to be looked into with, but the kind of the advantage, there's lots of plus and minuses, it's really complicated. But you know, what you're trying to do is, as I said, highlighted, you're trying to align people's kind of, you know, reward people for kind of helping the system and not versus when it's not. And at the moment, there's not any of that. There's not really that, and it's left to the ESO as its role of residual balancer, which is seeing kind of costs go up and up and up because the operation cost, just because, you know, the market isn't really incentivized to help solve these problems. And you've got, you know, the operation costs of what are they now, 2 billion something? They're just massive. But trying to align kind of operational, kind of these operational costs and kind of pass them on, because the market will be much better solving them than the ESO probably. You know, especially if it can solve it further ahead of real time.
So a slight challenge though on this idea that energy pricing itself is essential, because we see an issue with energy just being the sole thing rewarded for renewables and the subsidy regime, and renewables are not rewarded for operability. So on the one hand, there's a strong argument for increasing exposure, the demand, and giving them pricing wants to behave, but we also need to move away from an energy only pricing regime for renewable generation.
Yeah, completely. Renewable generation, high flexible, very, very capable stuff. From the ESO point of view, not at all.
I mean, these fundamental problems with some of the generation is low capital cost, high operating cost, and the other high capital cost, very low operating cost, and we, you know, the energy economists need to square that until we've got CFDs perhaps for a greater section of the renewables. But it does feel like moving away from energy only pricing. I think that was your point, because where and when you consume your energy is going to be as important as how much you consume, and rewarding flexibility either on the generation side or in storage or in the demand side is one way to drive some of the cost out of the system, and particularly reward customers who are prepared to be flexible.
I fully agree with you. I think renewables are capable of doing much more than just supplying energy in there. If they can divert their power to provide stability services or flexibility, as you've spoken about, I think we could really be driving the system costs down. But the way the current regimes are set up, your renewables role is defined as mostly as an energy generating unit. So I think that needs to change, and they have to be incentivized in other ways, either through requirements placed by ESO or the markets, aligning the different, like the pathfinders with the CFD rounds, for example, so that if someone is building a big generator, they can build a business case to say it's not just generating, it's going to provide restoration services, stability services, but there is an aligned bid that can help give that assurance on the business case, because otherwise it's really hard for someone to make that investment to provide that service, and then during the operation incentivizing them to provide services rather than just using energy would really help solve some of the challenges.
And I think that's in the room where the capital floor is heading to, as opposed to the CFD, to try and look across more than just energy as the value stream.
Of the deemed generation, for example, where you're based on your output potential, you're paid, but you can do anything.
But that's going to be so hard to monitor though, because then you have to look at
I think we could
how windy it might have been at that particular point. So we've discussed two of these, decarbonisation and decentralisation. This question is around digitalisation, and whether the development of digitalisation is happening fast enough and in the right way.
it's fast, happening really fast outside the power sector. That's the side, but the honest truth. So before I joined Renewables, my role was in innovation and delivered a project on digital substations, and it was fascinating to see what can be done with digital technologies, what it can achieve. And we still install meters which do a voltage multiplied by a current calculation, and we put an enormous amount of regulation around it. So there's the right reasons why digitalization hasn't just taken over power sector, because cybersecurity and data accuracy and assurance is quite a big concern. And if things go wrong, they can go really wrong. And we know of some blackouts that have happened because of not cybersecurity, not digitalization. However, things have moved on. It's just how do we bring that pace of change in the power sector, which is traditionally not really relied on digital technologies. We still call up and do a lot of our, critical action execution of the telephone. How do you do that when there is nobody sitting on the television waiting to take it? It's not all of the sites are, and they're not. There's not a person present. So I would say that it needs to change. It absolutely needs to change. We probably need to take a lot of help outside the industry. I just don't know who and how can really drive that.
It's obviously huge interest in digitalization. Most of the vendors have something they wish that network operators and others would buy. I think there's some very interesting points you're making about the humans in the loop and control system. We have talked already about how much faster or flighty or agile the system will become. We're going to have much better situational awareness tools and control rules that allow operators to see what's happening, but also much better decision support and a much higher degree of automation to cope with that system. So undoubtedly, I think in control rooms of networks, there's going to be much greater digitalization. I think a danger is that we might end up warehousing large volumes of data, not knowing what the information buried within it is going to be. So actually articulating clearly what the value proposition of that data is. That's maybe why some of this digitalization is not rolled. Yes, we could monitor voltages and currents up and down the system, but what are we actually doing with it? And it might well hinge a lot on understanding human behavior. National Grid ESO are very good at telling us, predicting what the electricity consumption will be of the national population hour by hour. But in the future, we'll have to know much greater granularity. What's happening within that street? Are we going to overload a local substation because the amount of electric vehicle charging or whatever? If we ask that street for demand side response, are we going to get it because there's something happening in the weather situation or the local sporting event or something that gets in the way? So much finer grade understanding of human behavior and how human behavior tracks to the use of service and tracks to the use of energy. It's probably one of the big use cases for digitalization.
I think it's interesting now. Two things that I would observe on that. One is something that you said, Laura, when we spoke last week around demand-side response and effectively over delivering, that everybody suddenly responds to the same signal and you go way the other direction. And I think the other challenge in here is something we've seen in financial services markets, although it has a lower consequence there. Once you start getting into the realms of everything being very digitized, algorithmic trading, that you can get some really unhelpful cascades happening there, which when you're talking about physical systems that have physical safety implications rather than just losing some money, could be quite serious.
Can I agree?
Absolutely.
Absolutely, yeah. It's digitalization is happening fast in the industry, it's keeping up with, and we've not, well, the ESO has not had a great track record of implementing IT change either, which has got to change because, as you say, the number of kind of people that the quality of the IT needs to be much better. But anyway, that's absolutely a challenge that we can recognise and facing up to. But the flip of that, absolutely, as you said, if you have everyone kind of responding to the same price signal, that's actually a challenge itself. You have it in generators, you have it in consumers, you have it in interconnectors. At the moment, you have the interconnectors flipping at the same time, and that's a massive challenge. You have how many 5 gigawatts, whatever it is, on the interconnectors. Effectively, if they flip all of them at the same time, so they've got the same price signal, IGB price signal, as a 10 gigawatt swing or whatever it is, And that's very hard from an operational standpoint. Because what you do is when you kind of looking at the system, you kind of have, right, the system's we're going to think it's going to do this much, then have reserves, and have kind of upwards and downward margin that you want to operate the system to. And so you can kind of effectively drive the system between these two boundaries. But when you have this potential for these massive swings, that is as you said, the megawatts. If you haven't got enough megawatts, that's the problem. If you've got too many, that's also a problem. So it is absolutely one of the emerging challenges, and don't know how to solve it at the moment. Like with many of them, unfortunately, but it is absolutely something that we've got to figure out. Because if everyone does switch on and off, think about the EVs we've got in the system. If they all switch on and off at the same time, that would be far bigger than the larger loss on the system, and that will cause some potential issues there. So yeah, absolutely.
Okay, I can see the little bubbles moving, so I think time to go to takeaways. Do you want to tell us your key takeaways, or should I read out the one that you've given? Please. These apparently are your key takeaways. They're putting words in your mouth. Unless you want to jump in and say before I put words in your mouth.
I think, yeah, sure. I think I did remember the exact words. I know that and stuff like that. I said vendors and OEMs need to facilitate better models. So we did speak about models quite a bit today. For national grid, yes, to be able to study and plan for future system stability issues, because we have spoken about this point many times today, and that is actually the key to understanding the future system behavior. Only when we understand something, we can prepare ourselves for it. And the second one I said is that grid forming converters should be incentivized to market mechanisms for renewable generators to be able to support grid stability. And this goes back to a lot of points we said, not just incentivized to generate, but to provide services. And how do we incentivize converters to behave and come and meet halfway the grids, and as the grid evolves to accommodate more converter distribution. Those are my takeaways.
And they were nice and specific. I think mine are a bit high level and possibly vague in comparison. But anyway, I said what I said. So the first thing I said was this really has to be a cross-sector effort between everybody who has a piece of the jigsaw, the developers, the OEMs, the grid operators, the research community. We have to find the solutions to how do we operate grids at 100% renewables, and as an effort that drives towards a lowest system cost, and that has to be through collaboration. And the other things that came up in the question a bit, this agile cycle of fundamentally rethinking the way we approach some of these problems and getting away from simple machines, and quickly putting some of those ideas into practice so we can learn how effective they are, how cost effective they are, and running around that cycle rapidly in order to drive innovation.
It's all right. I think so. There were, for me, there were the two takeaways. There were one, we very much want to engage with market parties to figure out the solution very much. If you've got a solution, we would love you to come and help us solve it. So there's kind of two things. One, we published a document called the Operability Strategy Roadmap, Operability Strategy Report, and the Markets Roadmap. The Operability Strategy Report says this is what we need, and the Market Roadmap says, and this is how this is how we'd like people. This is where you can, if you want to sell us a service, we'd love you to come and kind of point you at. This is how we're going to answer that need. So that those two documents are kind of aimed at potential service providers to come along and figure out where they're best suited to help us. The other one, very much for the kind of stakeholders in the room, is a stability market. So the stability market work is kind of coming to fruition. We don't have a stability market at the moment. There's not one ever anywhere in the entire world, as far as I'm aware. This is kind of the ESO working with the market to figure out how we actually put in a stability market. So this is, I think, is going to be concluded in November, December time. But there's very much, if you want to help shape that, then undoubtedly be next steps after November, December, because this is something that will come in, I'm guessing 2026, whatever. I can't remember what the timescales are for delivering it. But this is, if you want to sell a services, sell into stability market, have a look at that work. That'd be awesome. First versus the, if you want to sell services right now, have a look at the profitability strategy report, straight market roadmap. And you know, those will be the two key takeaways for anyone who can help.
So I don't have reading what our delegates think about, do you think that it can help me out with that?
Sector echo is looking like it's looking at foreign votes, and then vendors no ends, and then it's equal between grid form, agile cycling, and top of the strategy.
This is like the very bottom line field.
It is, it's quite hard to read, yeah.
Okay, perfect. So, I mean, I suppose what I've taken away from this conversation is that the grid is evolving really fast. And there's a big challenge in how to build this virtual circle between taking the need that's evolving and not a static thing, taking the developments that are happening within the OEM space, which is also not a static thing, they're happening quite rapidly, and building this virtual circle where these things are reinforcing each other rather than holding each other back, I suppose. That there's a huge amount of modelling needed to be done to really build insights into this rapidly changing system. That, as Tim said, the system is getting lighter, faster, and lightier. So I think that's actually a really good way of describing it, rather than being sort of relatively deterministic and based on these big, heavy lumps of metal, which we all understand pretty well and have a comfort blanket relationship with. And we've got to get used to things being run in a lighter, less substantial way almost. I think kind of feels that way. But these things are really important. You know, there are real safety implications of getting it wrong. This isn't just a nice to have in terms of doing it correctly, it's absolutely essential. And so, although we might feel a desire to rush forwards, that, you know, it feels to me as if it's entirely reasonable that actually we're taking a breath and making sure it's being done safely and properly, because the consequences of not doing that, you know, and as I think as Will said before, 140 kilovolts is kind of like quite a scary thing. And so, you know, that's not no small responsibility that ESO has to manage. So I would really like to thank all of our speakers. Will from ESO, Tim, so you changed, didn't you? Imperial College now, and Priyanka from Scottish Power. I'd like to invite you all to come to the next event and our final event of the year, which will be taking place on the 1st of December, which is going to be effectively summarising all the things that we've been discussing through the different sessions this year. And I think that's going to be at a different, new and innovative time, isn't it? It's going to be a late afternoon.
Yeah, 4:30 start.
So that would be no breakfast. But maybe some wine. Yes. So what more incentive could there be? And indeed, we would welcome feedback on the events. I think there's normally an email that goes around so people can leave their feedback. And also I would like to thank the sponsors, so Energy Institute, for hosting us for this event.